Good morning, students. Today we study new chapter Oscillation. I am Aher from RBNB College, Rampur. Now we study the chapter Oscillation. In this chapter we study the various motions. Now in this case we see the motion oscillatory motion. Now the first we see periodic motion. Periodic motion. Periodic motion is the motion in which the particle or any motion which repeats after equal interval of time, it is called as periodic motion. For example, suppose planet moves around the earth, planet moves around the sun, it is the periodic motion. Now moon is revolved around the earth, it is periodic motion. That is, any motion repeats after equal interval of time, it is called as periodic motion. Now the next motion, that is oscillatory motion. Oscillatory motion. Oscillatory motion, it is the motion in which in oscillatory motion the object moves to and fro about the mean position. The motion is oscillatory motion. Suppose we consider example of simple pendulum. In this case, the simple pendulum, suppose this is the simple point pendulum. This is the simple pendulum, this is the rest position. If we release the simple pendulum through some angle, it performs the motion. The motion is oscillatory motion. The motion is oscillatory motion. That is, this is called as mean position. That is, the motion or the displacement is 0 here. Now, suppose this bob of simple pendulum is released through some distance theta or through some angle theta, it performs the motion, that is to and fro motion. This type of motion is called as oscillatory motion. In this case, the bob moves to and in backward motion about this mean position, it is called as oscillatory motion. In case of oscillatory motion, the motion is to and fro and it is periodic. That is, any motion is periodic and it is oscillatory. The motion is called as simple harmonic motion. The motion is called as simple harmonic motion. Now we see the next type of motion, that is the motion, it is called as, suppose the velocity, displacement and the acceleration, these are the physical quantity. These are minimum or maximum at a certain point, at a certain angle. These are called as harmonic function. That is, these are the minimum and maximum value of velocity, acceleration and displacement is given by sine and cos theta. Sine theta and cos theta. This sine theta and cos theta are called as harmonic functions. Harmonic functions. Now these harmonic functions are the motion, it is in between these, due to this harmonic function, it is called as harmonic motion. Harmonic motion. Harmonic motion, and suppose the motion is periodic, it is oscillatory, it is minimum and maximum about mean position, it is called as simple harmonic motion. It is called as simple harmonic motion. Now see, what is the linear motion? The motion is along the straight line, it is called as linear motion. Motion along the curved path, it is called as rotational motion or curved angular motion. Now in this case, in this chapter, we see periodic motion, combination of periodic motion and oscillatory motion. Suppose, for example, we consider a simple pendulum. In case of simple pendulum, the pendulum is at rest. This is called as mean position. If this simple pendulum is released through some angle, it performs the motion. This type of motion, it is called as oscillatory motion and it is periodic. Hence, the motion of simple pendulum, it is called as simple harmonic motion. And in this case there is displacement, velocity and acceleration. They are represented by sin theta and cos theta. Sin theta and cos theta are called as harmonic function, and the motion is such a type, the motion of this type, it is called as harmonic function. The motion is harmonic motion. Now see, suppose this type of motion, it is due to harmonic function, the motion is called as harmonic motion. Now in case of simple harmonic motion, any motion repeats after equal interval of time in which the object moves to and fro about a certain path, about a fixed path, the motion is simple harmonic motion. It is denoted by SHM. The simple harmonic motion is the motion, it is the periodic motion in which object moves to and fro about its mean position along a certain fixed path. It is called as simple harmonic motion. Now there are two types of simple harmonic motion. The first is linear simple harmonic motion. Linear SHM, that is linear simple harmonic motion, that is particle performs motion along straight line, that is simple harmonic motion along a straight line. It is called as linear simple harmonic motion. Second type, the angular simple harmonic motion. Angular simple harmonic motion. Now in linear simple harmonic motion, in this case the motion, simple harmonic motion is along the straight line, and in angular SHM the motion performs, the motion of the object, it is along the curved path and it performs simple harmonic motion. It is angular motion. For example, the linear simple harmonic motion, here we consider, suppose a block is tied or attached with a spring, and if the spring is stretched or compressed, the motion of the spring, it is linear simple harmonic motion. Linear simple harmonic motion. Hence we define simple harmonic motion. What is the simple harmonic motion? In simple harmonic motion, the motion is periodic and it is oscillatory. Therefore, a periodic motion in which object moves to and fro about its fixed path along the certain fixed path along the straight line, it is called as linear motion. Now there are two types of SHM, linear SHM and angular SHM. Now here we consider the explanation of linear simple harmonic motion. In this case, suppose we see this is the zero displacement, this is the maximum displacement, and the displacement or velocity varies from minimum to maximum. This type of function are in case of sin theta and cos theta. These functions are called as harmonic function and the motion is called as harmonic motion. Now we see the first type, linear simple harmonic motion. Now here see, the particle starts from here and completes half vibration, again it completes the full vibration, that is the complete vibration. We can see here the period. The definition of period, that is period is the time taken to complete one oscillation. Time taken to complete one oscillation, it is called as period or periodic time. Now the frequency, definition of frequency, what is the frequency? It is number of oscillation per second per unit time, it is called as frequency. It is called as frequency. Now in this case we see the linear simple harmonic motion. In case of linear simple harmonic motion, we take the example of, see the picture, see the figure, in figure B, the spring the block is attached to the spring. Block is attached to the spring. In this case, the force is 0. That is, it is at rest. It is at rest. No any force acting on this block. Now, in this case, displacement is also 0. Now, in case of in figure B, the block is pulled towards right through some displacement, and there is the force or the displacement is x here. That is, this block is displaced through displacement x, and if the force is removed, the block tries to regain to its original position, and this force is due to elasticity. It is called as restoring force. Therefore, this restoring force is represented by F, and it is towards mean position. It is towards mean position. Now in figure C, see the block B is compressed. The spring and block is compressed. In this case, again there is a displacement that is in the negative direction, in the opposite direction, and displacement is x. Therefore, there is again, if we remove the force, the block tries towards the right, and the force is restoring force. It is called as restoring force, and it is towards mean position. Now see, in 3 cases, this is the equilibrium position. It is called as mean position. In this case, the block is tied towards the right. There is a force, restoring force developed in string, and it is again, if the force is removed, it is towards mean position. That is, we can say this force, restoring force, is directly proportional to displacement. Now in case of C, suppose this block is compressed, then there is a displacement in the negative direction. Again the force is towards mean position. In both cases, the displacement, the restoring force is directly proportional to displacement. Again here, the displacement is, the restoring force is directly proportional to displacement, but this force is in the opposite direction. This force is in the opposite direction. Therefore, we can define the linear simple harmonic motion here. See again, the figure indicates this is the mean position, that is, it is the rest position where F is equal to 0. Now in case of E, the block is pulled towards right. Block is pulled towards right, that is, it is through displacement x. Due to elasticity, there is a force generated, the force is exerted. In this case, it is called as restoring force. This restoring force, it is towards mean position, it is due to elasticity. Now, if the spring is compressed, again there is a displacement, it is in the negative direction, and force is towards mean position. From this conclusion, from this above consideration, we can say the force developed in the spring, it is called as restoring force. The restoring force is due to elasticity. Restoring force is directly proportional to, x displacement, and it is towards, or it is in the opposite direction. That is, we can say that the F is directly proportional to minus x. We can write here F is equal to minus kx, where K is called as proportionality constant, and it is given by F upon x, that is magnitude of the force is F upon x, and it is called as force constant. K is called as force constant. And the SI unit of this force constant is, SI unit of force is Newton, SI unit of displacement is meter. Therefore, the SI unit of the force constant, proportionality constant, it is called as force constant, and the SI unit is Newton per meter. Now, according to Newton's law, again we can say, we know according to Newton's law, we can write here F is equal to ma. where F is force, m is mass, a is acceleration. Therefore, acceleration is equal to F upon m. F upon m. We can write here the value of F, it is minus kx. It is minus kx divided by m. Acceleration is equal to minus k upon m into x. This is the constant, and this constant k and m are constant here. We can say that acceleration is directly proportional to displacement. It is in the opposite direction. That is, the restoring force and acceleration, they are in the opposite direction that of the displacement. The magnitude of the force and acceleration, it is directly proportional to displacement, but the direction is in the opposite direction. This is the characteristic of linear SHM. Hence, we can define linear SHM. In linear SHM, it is defined as it is the periodic motion. It is the periodic motion in which object moves to and fro, and in this case the restoring force, the magnitude of restoring force or acceleration. Here we see the magnitude, that is, there is no minus sign. Suppose we consider magnitude there, the negative sign remains in the mind, and we can say that the restoring magnitude of the restoring force or acceleration, it is directly proportional to displacement. First criteria, it is directly proportional to the restoring force is directly proportional to displacement, and the direction of restoring force and this displacement, it is in the opposite direction. The motion is called as linear simple harmonic motion. That is, in this case, the motion of this block, it is along the straight line here. Now this is the mean position, this is the extreme position, this is the negative extreme position. In this case, the block moves about the mean position, that is positive extremity, and negative extremity, that is along the certain fixed path, along the straight line. The motion is called as linear simple harmonic motion. That is, we can define here linear simple harmonic motion. In linear simple harmonic motion, the magnitude of restoring force or acceleration, it is directly proportional to displacement of the particle, and its direction is opposite that of restoring force. The motion is called as linear simple harmonic motion. What is the simple harmonic motion here? Firstly, the motion is periodic, then the motion is oscillatory. The simple harmonic motion, it is the combination of oscillatory and periodic motion, but not all oscillatory motions are periodic, but oscillatory motions are periodic in every time, but circular motion, suppose this is periodic motion, but it is not oscillatory. See the definition of linear SHM here, that is the motion of particle, the motion in which the restoring force or the acceleration, it is directly proportional to the magnitude of the restoring force, and acceleration is directly proportional to displacement, and its direction is opposite that of force and acceleration. The type is, or this is called as linear SHM. Now in this case, we obtain the equation for differential equation of linear SHM. Then next topic is differential equation of linear SHM, it having 2 marks weightage. Now here we can see obtain the differential equation of linear SHM. Then here we consider, we know in linear SHM in linear SHM, it satisfies two conditions. In linear SHM satisfies two conditions. The first condition is that is the restoring force, magnitude of restoring force is directly proportional to displacement, and magnitude of or the force, direction of force, it is opposite that of displacement. Therefore we can totally write F is directly proportional to minus x. Here F is equal to minus kx. F is equal to minus kx. This is equation number 1 here. Now according to Newton's law of motion, in this case F is equal to, we can write here, mass into acceleration. This is equation number 2. Then in this case the RHS, it is force. We can equate this equation 1 and 2. Therefore from equation from 1 and 2 we can write here minus kx is equal to m into a. We can simplify the equation we get, that is minus ma is equal to minus kx. We can write here ma plus kx. Now m is mass, a is acceleration here, and we know what is the velocity here. What is the velocity in this case? We can write the x is displacement, velocity is equal to, it is rate of change of displacement, and acceleration is it is rate of change of velocity. Therefore acceleration is equal to dt of dv by dx. Therefore we can write here a is equal to d2x by dt square. Substitute the value. In this case we get m into d2x by dt square is equal to minus kx. Then m into d2 by dx by dt square plus kx is equal to 0. Rearrange the equation, we get that is d2x by dt square plus k upon m into x is equal to 0. It is called as differential equation of the linear SHM. See again, the differential equation of linear SHM. In linear SHM, the restoring force is there are two conditions. The restoring force is directly proportional to displacement. The restoring force and displacement are in the opposite direction. Therefore we can write F is directly proportional to minus x, F is equal to minus kx. According to Newton's law, F is equal to ma. Substitute the value of a here, we get d2x by dt square plus k upon m into x. It is called as differential equation of linear SHM. Now we derive the equation for displacement, velocity and acceleration. Now we find the expressions for, on the basis or according to the differential equation. Expression for acceleration, velocity and displacement. displacement. Firstly, we find the expression for acceleration here. Expression for acceleration. Here we can write expression for acceleration. Expression for acceleration. We know the differential equation for linear SHM. It is, that is, we know d2x by dt square plus k upon m into x is equal to 0. Again we can substitute here k upon m, it is nothing but omega square or under root k upon m, it is equal to omega square. Substitute here, we get d2x by dt square plus omega square x is equal to 0. Then we get d2x by dt square is equal to minus omega square x. Now this is the second derivative of displacement and it is nothing but acceleration. Therefore we can write here acceleration is minus omega square x. This is the value of acceleration. This is the value of acceleration. Omega is constant here. We can say that this acceleration, magnitude of acceleration is directly proportional to displacement. Acceleration and displacement are in the opposite direction. Next derivation is for expression for velocity. Expression for velocity. Again we consider the differential equation. The differential equation is given by differential equation. Differential equation is equal to, the differential equation is d2x by dt square plus omega square x is equal to 0. Is equal to 0. Consider this equation, rearrange for d2x by dt square which is equal to minus omega square x. This is the second derivative of displacement and we can write here it is again acceleration is equal to minus omega square x. But the acceleration, definition of acceleration is rate of change of velocity. Rate of change of velocity. Substitute the value of acceleration here. We get dv by dt is equal to minus omega square x. Now here multiply by with dx, divide it is by with dx, we get dv by dx multiply by dx by dt. Here see dx get cancelled. The remaining quantity is dv by dt which is equal to minus omega square x, which is equal to minus omega square x. Now here we can write the value for this, that is dx by dt, it is rate of change of displacement, it is nothing but velocity. The rate of change of displacement, it is the velocity. Therefore we can write it is dv by dx into v is equal to minus omega square x. We can write here v into dv by dx is equal to minus omega square x. Rearrange the equation, we resolve or we solve for v, and next expression is, see, v into dv by dx is equal to minus omega square x. Now separate variable method, write the separate variables, that is v into dv is equal to minus omega square x into dx. Then integrate from both sides, we get, integrating from both sides we get, the integration of this v dv, it is v square by 2 is equal to omega square. Here omega square is constant, integration of x dx. Therefore we can write v square by 2 is equal to omega square x square by 2 plus c, where c is constant here. C is called as integration constant. Integration constant. We find the value of integration constant here. Now see, in this case, consider x is equal to a, that is plus or minus a, that is it is the positive amplitude or negative amplitude, and velocity at extreme position. At extreme position, the x is plus or minus a, velocity is 0. Velocity is 0. Substitute the value of velocity is 0 here. We get 0 is equal to minus omega square a square divided by 2 plus c. Therefore, rearrange for c. C is equal to omega square a square divided by 2. Substitute the equation we get here. Substitute the equation. Then v square by 2 plus v square by 2 plus, which is equal to minus omega square x square by 2 plus omega square a square by 2. Rearrange 2 gets here cancel. We get v square is equal to minus omega square x square plus omega square a square. We can write here v square, it is omega square a square minus x square. A square minus x square. Therefore, v square is equal to, we can write, or for v, we can write plus or minus omega under root a square minus x square. A square minus x square. This is the expression for velocity. This is the expression for velocity. Now we find the expression for acceleration. The expression for displacement. Expression for displacement. Expression for displacement. We know velocity, magnitude of velocity, v is equal to, we have the value v is equal to plus or minus omega under root a square minus x square. A square minus x square. We consider only magnitude here. V is equal to omega a square minus x square. Therefore, we know the velocity, it is again rate of change of displacement. We can write here dx by dt, which is equal to omega a square minus x square. By separate variable method, we can write here dx by a square minus x square, which is equal to omega dt, which is equal to omega dt. Again, integrate from both sides. Integrate from both sides, we get the integration for this term, it is sine inverse. It is sine inverse x upon a is equal to omega t plus phi. Omega t plus phi. Here we can write, rearranging the equation, we get x is equal to a into sine of omega t plus phi. It is the expression for displacement. X is equal to a sine omega t plus phi, which is the expression for displacement. Thank you.